Hi, welcome back. We're going to take a look at the 2015 differential equation. Now, if you look at this equation right here, this one was a very hard one on the AP because this one is too tough to solve for our class, for what we're trying to do in here. And it takes too long, so the AP will give you a question like this, but they're not going to ask you to solve something like this. And the reason why is because of the subtraction. Sometimes people think, oh, I can bring the y over by adding it, and I would get y dy equals 2x dx. But that is not the case. If I were to add y, we would get dy plus y equals 2x dx. And this right here, you don't want to try solving that one. That is not very friendly to solve. So the AP won't ask you to solve a question like this right here. But they will ask you to apply it, and that's what they're asking us right here. So for part A, they ask us to sketch the slope field at the given point. So we're going to go and do this. Now notice there's nothing on the x-axis, so we're not going to put it there. And I'm going to go ahead and start at the point 0, 2. To get the slope, I just plug this in. This becomes 0 minus 2, or negative 2. Again, you don't have to be perfect. There's negative 2. Let's see, the point, what's the next point we could use? 0, 1. My slope, if I keep going, just going down, that just becomes 0 minus 1, or negative 1. Slightly less steep. Next one would be 0, negative 1. Our slope here would be 0 plus 1. Well, that's positive 1. And there we go. Add sound effects. Our next one, start up here, would be 1, 2. If I plug this in, we would get 2 minus 2, which is 0. So horizontal. At the point 1, 1, our slope will be 2 minus 1, which is 1. And the next one is at 1, negative 1. Our slope here would be 2 plus 1, which is 3. That's going to be pretty steep. There we go. And there's our graph. And there it is. Now the AP would probably make this worth 1 or 2 points, right there. Pretty easy to do. All right, now for part B, take a look here. They want us to find the second derivative in terms of x and y. We'll talk about what they mean by that in just a moment. And then it says to determine the concavity of all solutions in quadrant 2. So the first thing we're going to go ahead and do is find the second derivative. That's not terribly hard to do. We've done this many times last semester. So we're going to take the second derivative with respect to x. We're going to take the second derivative of y with respect to x. So that becomes 2 minus dy dx. Oh, notice this is implicit right here. So we're going to replace it. So therefore, our second derivative will be 2 minus, what is dy dx equal to? I can just replace it with this 2x minus y. So therefore, our second derivative would be 2 minus 2x plus y. So there's our second derivative. Then they mentioned something about concavity of the second quadrant. Well, if I'm in the second quadrant, notice I'm only going to look at the signs. So I want to know what the sign of the second derivative would be in quadrant 2. So I look over here in quadrant 2. I know that my x's are positive. Sorry, my x's are negative. Y's are positive. Boy, I'm on fire today. If I knew how to edit, I can edit that mistake out. But we're not going to worry about that right now. So in quadrant 2, because the x's are negative and the y's are positive, we're going to go ahead and plug this in. So if we do that, our second derivative, we would get 2 minus, be careful, 2 times, remember this is a negative x plus a positive y. And if I simplify this, this becomes 2 plus x, 2x, plus y. Notice, this is always positive. This is going to be positive. This is going to be greater than 0. So what can we say? Well, that's greater than 0, so we know it's going to be concave up. So we can say all solutions in quadrant 2 are concave up. And that is because the second derivative is greater than 0. Piece of cake. All right, for part C, let's take a look. It says, let f of x be a particular solution to the differential equation with this initial condition. Does f have a relative minimum, maximum, or neither at x equals 2? Now, this is where people in the AP messed up. They kept trying to solve it. And remember, we talked about, you don't want to try solving this one, okay? They're not asking you to solve it. They want to know if we have a relative maximum or minimum. Well, for that, I know I can find out my derivative. If I find my derivative at that point, dy dx, at the point 2, 3, let's find the value of the derivative. So remember, my derivative was just 2x minus y. So it'll be 2 times 2 minus 3, which is 1. So let's go back. For neither, you really need to check the first derivative. You want to check if that's a critical number. Notice when I plugged it into my first derivative, I don't get 0. This is not a critical number. So therefore, this cannot be a maximum nor a minimum. So our answer would be neither in this case. And that is because the point 2, 3 is not a critical number. Now, here's the mistake that also happened on the AP. Students recognize, well, I can use my second derivative test. So if I plug in my second derivative at that point 2, 3, let's see what happens. There's my second derivative. We get 2 minus, that just becomes 4 plus 3. And I know that this is going to be 0. So a lot of people said that's going to be concave up. Therefore, we would have a relative minimum. But here's the problem with that. It's not a critical number. See right here where I draw concave up, to be a relative minimum, it has to be concave up, yes, but at that point it has to have a slope of 0. But at the point 2, 3, we know the slope is not 0. So that's why that fails right there. So if you just did the second derivative test, you could get a point for your work, but you're not going to get full credit because of not checking for that critical number. So the moral of the story, check that critical number right there. So we don't want to go straight into it. But this would work if 2, 3 was a critical number. So in other words, if it was a critical number, like if we got 0 here, then you would get this, then you would have to do the second derivative test. All right. And the last one, part D, it says find all of the constants m and n for which the function is a solution to the differential equation. Again, they're not asking us to solve it. They're asking us is that the solution is a line. The solution to the derivative, dy dx, is y equals mx plus b. Or, therefore, our solution is a line. So if our solution is a line, I know that my second derivative has to be 0. Remember, for a line, the first derivative is a constant, the second derivative is going to be 0. So if we look at a couple things right here, I know that my derivative dy dx is 2x minus y, and that our second derivative is 2 minus 2x plus y. Well, I know that this has to be 0. So if I solve for this, if I just look at my second derivative, I can therefore say y equals 2x minus 2. Well, there's my line. There's my line. So if I compare to y equals mx plus b, well, what is m equal to? 2. B is equal to -2. I hope you enjoyed this video. I will see you all later. Bye-bye.